All right, this is lesson 1.2, parent functions and transformations. First thing we need to remember is about domain and range. Domain, when we're looking at the graph, we want to look left and right. And then for our range, those are your y values, which is up and down. So domain is left, right, range is up and down. We've got 4 parent functions. A parent function is the main graph before we move it in any way or change it in any way. So the 4 parent functions, the first one we have is the constant. Here's the rule or the equation for a constant. F of x equals 1. In the graph of a constant, remember constant means never changing. So when we have the graph of a constant, it's literally just a flat line. So a way to remember this is literally straight, flat line. We do need to identify the domain and range of this graph. So first we'll look at the domain. Again, that's where we're looking left and right. If you'll notice, the graph goes to the left forever and it goes to the right forever. That means it literally touches every single x value, negative and positive. Negative and positive numbers all together, we call this all real numbers. It's like an R with an extra bar in there. Your range is where we're talking about your y value. If you'll notice that the graph only crosses the y value right here at 1, so your range is y equals 1. The graph never touches any other y value, only 1. The next parent function is linear. Linear you've seen before. The rule for linear, again, the rule just means the equation, the basic equation for linear. F of x, don't forget that's the same thing as y, it's a different type of notation. F of x equals just x with linear. And an example of what a linear graph looks like, it's basically any other graph you've ever seen in your whole life. It always crosses right at the origin, at least the basic linear graph does. And there it is. A way to remember this is a straight sloped line. We want to identify the domain and the range here as well. Again, domain, that's where we're looking at the graph from left to right. The graph is going left forever. It is also going right forever. If it goes in both directions forever, your answer is always all real numbers. Now the range. On the first one, the graph was straight. It only crossed the y-axis. It only had y values of 1. This guy is going up forever. It's also going down forever. So in this case, our range is all real numbers. If it goes in both directions forever, it's all real numbers. Okay, a new one on you. You may not have seen this before. It's called absolute value. Absolute value, the rule for this, f of x equals the absolute value of x. So these 2 bars, kind of like jail bars, those are absolute value bars, and this is a dead giveaway as to what type of equation you have. If you see these bars, you know you're talking about an absolute value equation and or an absolute value graph. The absolute value graph is also very easy to identify. Absolute value graph is shaped like a V. absolute value, the graph looks like a V. I guess you could just say a way to remember this would be a V-shaped graph. Again, we want to identify the domain and the range. So again, domain, we are looking left and right. If you follow this graph, it goes left forever. You can also follow it right forever. So your domain, again, is all real numbers. Looking at the range, this is where we're going to look up and down. The graph goes up forever in both directions. Doesn't really matter. It's just going up, and it goes up forever. However, when we follow the graph back down, we notice that it stops right here at 0, and it never goes below 0. So range is your y value. The entire graph is greater than or equal to, because it touches, 0. The entire graph is above the point of 0. Range is y is greater than or equal to 0. Lastly, our last parent function is the quadratic. Your equation for quadratic, f of x equals x squared. This one also has a dead giveaway. Anytime you see a variable squared, that tells you that we have a quadratic equation. Hopefully you remember what the quadratic graph looks like. Graph of a quadratic is what we call a parabola, which is basically a U. U-shaped graph. And I want you to remember what this is called. Parabola. Okay, again, we need the domain and the range. Your domain, that's where we follow the graph, left and right. If we follow it left, we'll see that it does go left forever, and we will see that it does go right forever. Your domain is all real numbers. The range, we are following the graph up and down. So if we follow the graph up, you will see that it does go up forever. However, when we start to follow the graph down, it does not go down forever. It stops going down at 0. So your range, again, that's your y, are all greater than or equal to 0. Okay, these are your 4 basic parent functions. A couple of ways to pick out which one you have. We're going to need to be able to identify whether we have constant, linear, absolute value, or quadratic. Again, the constant has a straight flat line. Your linear, that's a line with slope. Absolute value, that's easy. Value, the graph looks like a V. Quadratic, you've seen before. That's your U-shaped parabola. We also need to identify what type of equation it is based on what type of graph it is based on the actual equation. If you'll notice that with the constant, there is no x. There's not a variable of any sort. It's just a number. That's a dead giveaway that you have a constant graph. Linear is going to be a single x. It will not have a squared. It will not have absolute value bars. It's just an x. It can have numbers with it, but make sure that it is a single x. That will be your giveaway that you have linear. Absolute value, those are always easy to identify. They have the jail bars. And then your quadratic should be easy to identify as well, as it's always going to have the squared. All right, parent functions. These are your parent functions. These are the most basic, positive version of a function. Also, another thing to remember is it goes through all of these will go through the origin. That's a characteristic of being a parent function. Okay, transformations. We went over these on the first day of school. Hopefully you did. just a recap. Basically, if you think about going through a transformation, I always like to use the example of Bruce Jenner. He went through a transformation and he no longer looks the same. That's the exact same thing as what we're going to be doing with graphs. We can move them, change them, flip them, however we want. Transformation, in any way that you want to talk about it, pretty much means the same thing. So transformations in terms of graph, it just changes the size. It can change the size. It can change the shape, the position, or orientation. Okay, so a few of the basic transformations that we have. If we are going to move up or down, so any of the above graphs, we can move them up or we can move them down. As we talked about before, hopefully, this is a vertical transformation, or we call it, it could be called a vertical transformation or a vertical translation. Up and down, it's vertical. It's a no-brainer. If we want to move left or right, this is going to be a horizontal translation. We do have an option where we can flip the graph over. So if we flip it, another way to say a flip is a reflection. We can also make this graph wider, or we can shrink it and make it more narrow. So if we do that, we have what's called a vertical shrink or a vertical stretch, and these things make it wider and or more narrow. So if we're going to widen the graph, we can have what is called a vertical shrink. So what I want you to picture is I have this graph, and if I need to make it wider, I'm going to shrink it vertically. That's just like if you take me and you shrink me, I'm probably going to get fatter or wider. So we'll take this, if we shrink it, the graph is going to split and get wider. However, if we take this and we stretch it, then the graph is going to go from looking like a U of this sort to a more skinny U or a more narrow U. So the other option is a narrow. In that case, it would be a vertical stretch. So with transformations, we kind of start abbreviating the horizontal and vertical because it just becomes understood. All right, next I want you to grab your transformations handout, the foldable that you were given, the one that looks like this. It is a foldable, so fold it so that it works for you. This is something you're going to use all year. Do not lose it. It will need to be glued into your spiral at the end of the lesson. Believe me, this is not something you want to lose. We're not going to talk about all of these today, but we're going to go over about half of them. So you'll notice that it's a foldable and it opens, well, kind of. If you're OCD, you can cut this off. We'll open up, let's start with the horizontal translations. So again, that's when we're moving the graph left and when we're moving the graph right. Now, as we talked about, hopefully you guys had talked about this before. let me start on the front. We have a number that's going to be inside of something. In this case, these are absolute value bars. So you have your X, and also inside is a number. This is what tells you that you have a horizontal translation if you're looking at an equation. If you look at the vertical one, you still have your absolute value bars with X inside, but your number is going to be added or subtracted to the outside. So horizontals, we're adding or subtracting on the inside. Verticals, you are adding or subtracting on the outside. With verticals are the ones that are they're the most normal. So if you have a number on the outside and you are adding it, surely intelligence would tell you that the graph would likely move up. So it shifts up when you're adding. Outside. It will be outside of something, parentheses, absolute value bars, something. If we're adding and it goes up, then obviously it will go down when we subtract on the outside. Okay. Here's your example. So remember that the parent function was just the absolute value of X, and they've graphed this for you. Now they've given you the absolute value of X minus 5. So if we are subtracting from the outside, that tells me that this graph is going to go down 5 units. So literally every single point on this graph is going to shift down 5 units. So we'll start at the bottom of the V, 1, 2, 3, 4, 5. This point will move down 5 units. This one will move down 5 units. Every single point on this graph will move down 5 units. This guy, down. This guy, down. You get the point. This would be a vertical translation down. The graph originated here. This was the parent function. It just shifted down 5 units. Now, in contrast, if I put that positive 5 or I put the 5 inside the absolute value bars, now we're talking about going left and right. So again, if we have a number that's being added or subtracted on the outside, it's going up and down. If it is added or subtracted on the inside, it is moving left or right. This one is a little bit backwards. It will actually be moving right when you subtract. HIO, this means horizontal, inside, like we just talked about, and opposite. So I know that when you think about adding 5, that would probably make you think that you are moving right. In all actuality, you are going to be moving left if you are adding. Shift left when adding. And remember, this is on the inside. Horizontal, inside, opposite. Okay, an example of this, adding 5. If I'm adding, that tells me I'm going left 5 units. Every single point on this graph will move left 5 points. So we'll start here. It goes 1, 2, 3, 4, 5. This guy is moving left 1, 2, 3, 4, 5. This one, same thing. Same thing. Every point on the graph will move left 5 in this example. There's your translation. We took the graph, moved it left. All right, the next thing we're going to talk about is reflections. These are reflections in the x-axis. So we know that we're going to have a reflection because there will be a negative that's out in front. We'll either have a negative out in front, or we will talk about the other one next class. So at this point, anytime there's a negative out in front of the absolute value bars, or you may have parentheses instead, you know that your graph is going to be reflecting over the x-axis. Here's an example. Negative out in front of your absolute value of x. This is the parent function. And if we put a negative, then that means every single point is going to flip over the x-axis. This one's not going to flip anywhere because he's on the x-axis, but this guy will be reflected perfectly over the x-axis. So again, this is 1 point above the x-axis, so if I flip it, it'll be 1 point below the x-axis. This is a reflection, specifically over the x-axis. And we know that this is going to happen if you ever see a negative out in front. Way to remember this, your smile becomes a frown. In this case, it's a V. It's not really much of a smile, but you get the point. All right, the last thing we're going to talk about today on this foldable is your vertical stretch and your vertical shrink. So we've talked about if you have a negative out in front, that tells you that you're going to have a reflection. If there is a number, so your A, it stands for a number. If you have a number that's out in front, you're going to have a vertical stretch or a vertical shrink. The way you're going to know whether it's one or the other is dependent upon what that number actually is. Okay, so the parabola is going to be a vertical stretch. So if we stretch it vertically, it's going to stretch away from the x-axis. So here's my x-axis. If I stretch this guy vertically, my V is going to go from looking like this to more like this. That is away from the x-axis. The way you're going to know it's a vertical stretch is because that number in front is going to be greater than 1. A is a number, so a number greater than 1, or another option is what we call a Dolly fraction. Hopefully you know who Dolly Parton is. Fraction. Maybe I should learn to spell. Hopefully you know who Dolly Parton is. She is heavier on the top than she is on the bottom. An example of a Dolly fraction, 9/4. Heavier on the top than it is on the bottom. So if you have a fraction that's a Dolly fraction, then we're talking about a vertical. This guy is going to get narrower. Or, if you like to think of it this way, skinnier. Narrower or skinnier. So you can think of a rubber band. If you stretch it vertically, it's going to get more skinny or more narrow. Okay, the other option we have is what if that number is less than 1? That's going to give you your horizontal shrink. I'm sorry, I meant to say your vertical shrink. Shrinks towards the x-axis. So if I take that same rubber band and I squish it, this guy is going to get fatter. It's going to look something like this. Okay. You're going to know that you have a shrink if you have a number that's between 0 and 1. So it can't be negative because remember negatives are reflections. However, if it's less than 1 and greater than 0, so basically a fraction. But not any fraction. It can't be a Dolly fraction. So for these types of fractions, we call them J-Lo fractions. J-Lo's heavier on the bottom than she is on the top. An example, 1/2. So if your number out in front is 1/2, you know automatically that you have a shrink. This guy is going to get wider. If you like to think of it this way, the graph's going to get fatter. Okay, so just a recap. Adding and subtracting. If we are adding and subtracting on the inside, we're moving left and right. If you add or subtract on the outside, you're moving up and down. The other thing we talked about was this negative. Negative out in front means you have a reflection. Your graph is going to be reflected. The other possibility is you could have a number out in front. If you have a number out in front, then you're going to either have a vertical stretch or a vertical shrink. You'll know it's a stretch because your number will be greater than 1. You'll know it's a shrink because your number will be between 0 and 1. Okay, we're going to work a few problems that go along with this. So put this to the side. You're going to need it later. All All right, identifying / describing. Transformations. Okay, our first example. We've got f of x equals x minus 6. First thing we want to do, a couple of things. Step 1, we're going to identify the parent function. So remember, I talked to you about how to identify that. If we're looking at the equation, here, the front part of your notes, we've got x minus 6. So it's not a constant because constants don't have any x's. It could be linear. Linear does have a regular x. According to our problem here, it's definitely not going to be absolute value because we don't have any absolute value bars. It's not going to be quadratic because we don't have a square. So basically the only thing that we're looking at here is linear. That is going to be your parent function. Step 2. Now we need to know how it is changed. So remember, from linear, the original equation is just f of x equals x. That's the original equation. So step 2, we have to identify what's changed now. The way I like to have you do this is point out, like actually with an arrow. So the original equation just had an x in it. The problem that I gave you has an x minus a 6. That negative 6 is a transformation. It is not inside of anything. So remember, adding or subtracting, we're either going to be doing a horizontal translation, left or right, or up and down. So we know that we're going left and right if we're adding or subtracting on the inside. Up and down is adding or subtracting on the outside. With this problem, there is no inside. This negative 6 is by default on the outside. This tells me that I have a vertical translation. 6 units. Which way am I going? Up or down? Subtracting on the outside tells me down. So step 1 would be identify the parent function. Step 2, identify what is changed. This is what has changed, that negative 6. Step 3, describe the transformation. And that's what we just did. Okay, example 2. F of x equals x plus 4 squared. I want you to take a minute and pause this video. I want you to try this one on your own. Following the steps, first identify the parent function, tell me what is changed, and then describe the function. By all means, use your foldable to describe the function at this point. Okay, identifying the parent function. That's squared. That should tell you automatically that you're looking at a quadratic. Whoop, maybe I should learn to spell again. Glad I'm not a spelling teacher. Quadratic, and the original equation for a quadratic, f of x equals x squared. This is what we started with. Step 2 says identify what has changed. Again, we're going to use our arrows to point out that anything that's different. We started with x squared, and now we have x plus 4 squared. So the x was already there, so is the squared. It's this positive 4 that's changed. Step 3 is describe the transformation. Now again, adding or subtracting, we're moving either left, right, or up, down. In this case, we are adding on the inside. So don't forget, parabola shifts left when adding on the inside. So the guys on the inside are backwards. Remember, horizontal, inside, opposite. Adding on the inside actually means we're going left. This is a horizontal translation. Left. So all this means is our parabola shifted left 4 units. Example 3, h of x. Don't let that throw you off. It's just another notation. Same thing as f of x. H of x equals 3/4 absolute value of x plus 1. Okay, I'm going to do this one with you. First step, parent function. Jail bars, automatically, that tells you you have an absolute value parent function. And the original equation for absolute value, f of x equals just absolute value of x. Step 2, identify what is changed. Again, we're going to put arrows over anything that is changed from the original equation to what we have now. So originally we just had this portion, which means the 3/4 is new and the positive 1 is new. So this time we have more than one thing that's new, and that's fine. Each of these things are their own transformation. So we've been talking about adding and subtracting. There's a positive 1 that's being added to the outside. Outside means we're going up and down. This is a vertical translation, up 1 unit. Okay, so we've taken care of this one. Now the 3/4, that's a number that's out in front. You may need to pick up your foldable and take a look at it. Numbers that are out in front, we call that A. We need to know if it's a vertical stretch or a vertical shrink. So when I open my foldable, I'll see that if my A is greater than 1, I have a stretch. If it's between 0 and 1, I have a shrink, or the JLO fractions. This is a JLO fraction, heavier on the bottom than it is on the top. Also, 3/4 is between 0 and 1, it's a fraction. So, this is a vertical shrink by 3/4. And that's it. I'm going to give you one more. Again, I want you to pause the video and do it by yourself once I give it to you. This is example 4. F of x equals negative x plus 3 squared plus 1/4. Pause the video and try this one on your own. Okay, first step, identify the parent function. The squared. Squared is a dead giveaway. This tells you quadratic. The original equation for a quadratic, f of x equals x squared. Step 2, identify what has changed. We started with just x squared, and now we have x plus 3 squared plus the 1/4. Also that negative out in front, I just missed that. Anything that has changed or anything that's new, that negative is new. The positive 3, that wasn't there to begin with. Neither was this 1/4. Now I have 3 transformations, all of which have to be described. We can start with things that you're most familiar with. Adding things on the outside, and we've got something that's added on the inside. We know that things on the outside are normal, they're like they say they are, so if it's plus 1/4, that means the graph is going up by 1/4. So we have a vertical translation up by 1/4. Again, adding on the outside means we're going up. Adding on the inside, so I'm inside these parentheses and I've added 3. Anything on the inside means horizontal. Horizontal, inside, opposite. If I'm adding on the inside, This means I'm going left. Horizontal translation. Left, 3. The last thing I have to remember is that negative on the outside. That was something that you and I talked about already. Anytime you see a negative on the outside, that tells me automatically I have a reflection in the x-axis. That's what this negative is telling me. Three transformations, 1, 2, 3. I've described them all. Okay, adding on the outside means we're going up and down. Adding or subtracting on the inside means we're going left and right. If there's a negative out in front, that's a reflection. If you have actual numbers out in front, depending on what that number is, you could have a vertical shrink or a vertical stretch. I want you to take your foldable and glue it into your journal, and we will finish that up next class.